Today in Algebra 2, we're going to look at rules for transformations of functions. This is section 1.2 in our textbook. So our essential question that we're going to be answering is, how do the graphs of y equals f of quantity x minus h plus k, y equal negative f of x, and y equal f of negative x compared to the graph of a parent function y equals f of x? This parent function is whichever function that we choose to start with. Now, transformations can be broken down into translations, reflections, or stretches and shrinks. So we have three different transformations that we're going to be looking at. Each transformation can be either horizontal or vertical. So let's start by looking at translations. Translations of a function, either horizontal or vertical, are continued or contained in this equation. We have y equals f of quantity x minus h plus k. The part inside the parentheses that's done to the x before the function value or the function operation is applied is a horizontal translation. It will move it left or right depending on the value of h. K is our vertical translation, and it will move it up or down depending on the value of k. So let's look at an example of that. Here it says identify the parent function, find the values of h and k, state the transformations to get from the parent function to the given function. So in this case, this is our transformed equation, and we want to go back to the parent function. Since this is a square situation, our parent function is a quadratic function, or y equals x squared. And our translations are found here and here. So we want in our translations to be in the form of x minus h before I square it. So I can rewrite this as g of x equals parentheses x minus negative 1 quantity squared plus 2. So here's our value. Here's our value for h. It's negative 1. This graph is going to move to the left 1 unit. And our value for k is 2, so it's going to move up 2 units. Notice in our original form, when it says x plus 1, we can immediately say it's going to go opposite, it's going to go left 1 unit. Let's start with a different parent function. Let's start with the parent function y equals 2x plus 1, and we have the graph of that function right here, y equals 2x plus 1. We want to move this function or this graph down 3 units. We want to see how it changes, and then we want to write the equation of the new function. So I'm going to take a few of the points on this line, and I'm just going to count down 3 steps. I'm just going to move it down 3 points so we can see where our new function becomes. Okay? Now our rule says that all we need to do is change our k. So if this is our f of x, we want to take y equals f of x, and since we're moving it down 3, we want to go minus 3. So let's take our function 2x plus 1 and do that. Y equals, here's our f of x, 2x plus 1, and then minus 3, which simplifies to 2x minus 2. Let's see if that matches our graph. As we take a look at this pink graph here, our y-intercept is negative 2, so we're right here at negative 2, and it has a slope of 2. So our physical translation and our equation match. Now let's do another translation. This time let's do a translation of the same graph, y equals 2x plus 1. It's our function that we're going to be working with, and we want to move it left 3 units. So our equation for a translation left 3 units is going to be f of x minus negative 3, or f of x plus 3. in the more familiar form. So I'm going to take this equation and I'm going to change my x to x plus 3. So I have y equals 2 quantity x plus 3 plus 1. That's my essential transformation there. So my equation becomes y equals 2x plus 6 plus 1, or y equals 2x plus 7. Now let's go and let's do our transformation, and let's do it physically by moving our original function y equals 2x plus 1 to the left 3 units and see if that works. So here's a point. Let's move it left 3. 1, 2, and 3. And 3. And our new graph is right here. There we go. So it's parallel again, has the same slope, and this time we look and we see that our y-intercept is 7, which is what we expected from our equation. Reflections. Reflections over the x-axis occur when y is equal to negative f of x. That is, the y values all become their opposite. We take our f of x and we put a negative in front of that whole function. Reflections over the y-axis occur when y equals f of negative x. That is, the x values only become their opposites. Here's a picture of that. Reflections in the x-axis. Here's our original graph, y equals f of x, and our reflected graph right here. Notice that they are reflected over the x-axis, mirror images, and a point on the x-axis stays the same. It's our fixed point because it's already on the line of symmetry. Y equals f of negative x. Here's our original graph. And this time we're reflecting, we're making the x coordinate negative, so it's a reflection over the y-axis. So here's our reflected graph. And we go across the y-axis, across the y-axis, across the y-axis, and notice our point on the y-axis stays fixed. So that's really one way that we can recognize an x-axis reflection and a y-axis reflection, is what point is fixed. On the x-axis, it's the point on the x-axis that doesn't change, and a y-axis reflection, the point on the y-axis doesn't change. Okay, so what we want to do is a couple of reflections. We want to reflect the graph of y equals absolute value of x plus 3 plus 1 over the x-axis. So again, this function is our f of x. This is what we're starting with, and we're going to do a reflection over the x-axis. A reflection over the x-axis means I need to do the negative of f of x. So I'm going to take this whole function and do the negative of it. So y equals the negative of this entire function f of x. So when I do that, distributing the negative, I have negative, the absolute value term, and the negative of plus 1 makes it minus 1. So let's see if this graph looks right when I do the physical transformation here. I want to reflect this over the x-axis. So I'm going to take all of the points and just reflect over the x-axis here. So across the x, there's our new vertex. Across the x, across the x. Excuse me, that point's here. And this point is here. Here is our new graph. Okay. Notice our vertex has changed. Our vertex is now -3, -1, which matches what we know about our h and k here. So our vertex is -3, -1. We have a negative out in front here, which means we're opening upside down. And so this is a reflection over the x-axis of this graph. Okay? All right. Our reflection over the y-axis. Same graph. Again, this is our f of x. And what we're going to do for a reflection over the y-axis is the x gets replaced with negative x. So our new equation is y equals the absolute value of negative x plus 3 plus 1. It's kind of an interesting looking graph because all of a sudden we have a coefficient that's negative here. Let's take a look at what that looks like. We're going to go to our function here, reflect it over the y-axis. This one stays the same. Reflect this over the y-axis. And reflect that over the y-axis. And we have this new graph. Its vertex is now 3, 1. The x-coordinate of the vertex changed. It went to its opposite. It was, or in our original, at negative 3, 1. And our new one then is at 3, positive 1. So it changed it. It reversed the coordinate, the x-coordinate of the vertex, because x has been replaced with negative x. So if we look at where our vertex becomes, it's the negative 1. It's this value here divided by the negative 1. So negative 3. So it changes that. Okay? Now, let's see what a stretch or shrink looks like. Vertical stretches to a function f of x. We multiply the y coordinates by a factor of a, so we have y equals a times f of x. And the stretch or shrink is by a factor of a. Horizontal stretches to a function, we multiply the x-coordinate by a factor of a. So we get y equals f of a times x, and the stretch or shrink is by a factor of 1 over a. That's because on our horizontal ones, it always seems to be the opposite of what we would expect from the equation. It's because we compensate instead. Okay, so let's take a look at how those work. We want to shrink this graph. Here's our f of x. The graph of y equals absolute value of x minus 3 minus 5 horizontally by a factor of 1/3. We want to know what is the new equation. So that means we need to replace x with 3x. Remember, if the shrink factor is 1 over a, then we're multiplying the x by a. So our new equation has to be y equals absolute value 3x minus 3 minus 5. Now visually, let's see how this works. Remember, it says that we are multiplying all of the x coordinates by shrinking it by 1 over a. Okay? So let's see how that works. And that should also be a 1 over a. Yeah, that'll work. All right, so our shrink factor is 1 over a, and our equation, it shows up as just a. All right, so let's look at some points here. Notice on our graph, by the way, our graph is going by a scale of 2. So our ordered pair here, this is the ordered pair 3, negative 5. If I take the coordinates of this point and I take my x coordinate and I multiply it by our shrink factor of 1/3, this is what we get. So we have the 3, negative 5. We'll take the x coordinate of 3 and multiply it by 1/3 to get 1. So that gives us our new point of 1, negative 5. Let's look at another point. Let's look at this point, 6, negative 2. And let's look at, what would be another good point here? 0, negative 2. And let's do the same thing to those. Okay, so if we start with 6, negative 2, I'm going to take the x coordinate and multiply it by 3. So 1/3 times 6 is 2. And so I get the ordered pair 2, negative 2. And let's do the point 0, negative 2. I take the x coordinate of 0 and multiply it by 1/3, so it stays 0. And so I end up staying at 0, negative 2. So let's graph these points and see what it looks like. 1, negative 5, 2, negative 2, and 0, negative 2. We end up with a graph that looks like this. It's 3 times skinnier. We've done a horizontal shrink, which moves the two sides together by 1/3. So it's much skinnier on that one. Okay? And as we check these points, just to make sure they're on the graph, we can put 1 in for x, and we would get those values. When I put 1 in for x, I get 3 minus 3 is 0. Absolute value of 0 is 0, and then minus 5, so I get 1, negative 5. And we'll see that those points all satisfy that equation. Okay, so a stretch, this is our f of x, and we're stretching this whole function by 2. So that says we want to multiply the whole function by 2. So I'm going to go y equals 2 times the whole function, absolute value of x minus 3 minus 5. Distributing gives us 2 times the absolute value of x minus 3 minus 10. Let's graph that and see how that works. I'm going to take all of the y coordinates and I'm going to multiply them by 2. So let's take these 3 original points here, which were on our original function. 0, negative 2. Take the y coordinate of negative 2 and multiply it by 2. And that gives us our new y coordinate. Our next point for our new vertex, take the y coordinate of negative 5 and multiply it by 2. Gives us negative 10. So we have the ordered pair 3, negative 10. And then our last point, 6, negative 2. Take our y coordinate again and multiply it by positive 2, and we get negative 4. So we have the ordered pair 6, negative 4. Let's plot those points. Here was our point 0, negative 2. We multiplied our y coordinate by 2 to get 0, negative 4. Here's our point 3, negative 5. Take our y coordinate and multiply by 2 to get negative 10. So we're going to have to move down just a bit. 2, 4, 6, 8. Here's 10. And 6, negative 2. We multiplied our y coordinate of negative 2 by 2 to get negative 4. Negative 4. And here is our new graph. Okay. Not too far on that one. Okay, so you can see that the pink graph has been moved in sideways. It's shrinking it. Our point on the y-axis stay the same. In our vertical stretch, we pulled everything down, straight down, and we end up there. We do that. Make that graph just a little bit better here. Our points on the y, on our x-axis are fixed there. Okay? So that's our rules for transformations of functions. Whatever function we start with, we do those functions with them.